So we are missing the magnitude of tension 1, the magnitude of tension 2, and the angle of tension 2. So that's 3 unknowns. Ideally, we want to have 3 equations in order to figure that out. Because generally, as long as you have as many equations as you have unknowns, that tends to form a system that can be solved. So let's draw a free body diagram here. If we're dealing with just the bar as the objects we care about, since presumably that's the object with lots of forces acting on it that we care about here. So we've got this bar. We know its length is 1.5 meters. What forces are acting on the bar that we should consider?
Gravity at the center of mass.
Yeah. And how strong is the force of gravity going to be here?
60 newtons.
Yeah. That's given. The weight of the bar is the force of gravity. So force of gravity on the bar is 60 newtons straight down.
And then the child is 200 newtons down.
Right. So we got a force from the child's hand pulling down, and we know where that is as well. I guess that's 1.5 meters from the end of the bar. Do we know how long the bar is?
It's 1.8 meters.
Okay, yeah, that is given. So 1.5 meters from one end and 0.3 meters from the other end. And that's 200 newtons. So let's call that FC, the force of the child.
And then we have tension 1 and tension 2 pointing in the direction of the ropes.
Right. So tension 1, we don't know how strong it is, but we at least know it's at a 30-degree angle with the horizontal. In fact, it might be wise to just preemptively split that into components, because we're probably going to need it in component form later anyway. And we know it makes a 30-degree angle with horizontal. So let me write that in. 30 degrees. And we don't know how strong the force is, but we'll just call that strength T1 as an unknown. And likewise T2 at some of also unknown angle. Unknown magnitude and unknown angle. And presumably T2 can also be split into components. Even though we don't know what the angle is, we can at least write it in terms of its components. So T2 is going to have a Y component and an X component, even though we have no idea yet what the angle is. So let's go ahead and label these. In general, anytime you've got some unknown variables that you think are going to be important, I would recommend labeling them with variables. That way you can refer to those variables in the equations, even if you don't know their values yet. So theta 2, we don't know. And we could even label the unknown components, T1x, T1y, T2x, and T2y. Any questions on those labels so far? So based on this labeling system, how many unknowns do we seem to have at this point?
Like 5.
Yeah, we seem to have a lot of unknowns because we're missing the components. Mm-hmm. We're also missing the magnitudes, and we're missing this angle. So by labeling the components, it looks like we've increased the number of unknowns. Mm-hmm. But we can use trigonometry to figure out how those unknowns are related to each other. For instance, how would you write out the components of T1 in terms of the angle?
T1x would be, I mean, we could say negative T1 cosine 30, and then positive T1 sine 30 for y.
Yeah, that should work. And that way, we're at least writing these two unknowns in terms of the one unknown magnitude and the angle that we know. And sine 30, if I remember correctly, is 1/2. Cosine 30 should be square root of 3/2.
Can we also write like T1 and T2? Could we say FT1 and FT2 just so everything's forces?
Yeah, we're just using T1 as an abbreviation for the force of tension 1, but keep in mind it is a force.
Okay.
So it is some unknown number of newtons. But whatever that unknown number of newtons is, we take that times negative cosine of 30 degrees, and that'll tell us the x component. And that same unknown times positive sine of 30 degrees, and that'll be the y component. So that'll be negative root 3/2 times T1 and positive 1/2 times T1. So we can at least write T1 in terms of its x and y components. And we could even do the same thing for T2. Even though we don't know what theta2 is, we can at least rewrite its components. We can say T2x and T2y. How do we write the x and y components of T2 in terms of the magnitude and angle?
X would be T2 cosine theta2, and y would be T2 sine theta2.
Yeah. And even though we don't know what the angle is, we can at least write everything in terms of that unknown angle. So we can make those substitutions if needed. Any questions on that so far? And with those substitutions, even though we have these unknown components, we can at least write all of the unknown components in terms of only 3 unknowns. We don't know T2, we don't know theta2, we don't know T1, but we can write all of these components in terms of just those 3 unknowns. So we at least can, in principle, write out equations in terms of just 3 unknowns, which means we still only need 3 equations. And what could those 3 equations be? What equations can we guarantee should be true about this bar?
Net torque is 0 and net force is 0.
Yeah, so that gives us 2 equations. We know the sum of the forces must be 0. And how do we know that? How do we know the forces must add up to 0 here?
Because the bar isn't moving. Nothing's moving. It's
stationary. And not just not moving. It could be moving as long as it's not doing what?
There's no external. It's not accelerating, so there's no external force.
Right. The no acceleration is the important thing. And if it's not moving and it continues to be not moving, that means no acceleration and therefore no force or no total force on the object. But keep in mind, even if it was moving, as long as it's moving at constant velocity, you can still use this idea that the forces add up to 0. And since this is a 2-dimensional problem, the force equation is really 2 equations. The forces in the x direction add up to 0, and separately the forces in the y direction add up to 0. So we can split this into a force x component equation and separately a force y component equation. So if we list out all the forces with x components, actually, what are the only forces with x components here?
The 2 tensions.
Yeah, so we can just say T1x plus T2x adds up to 0. Since gravity and the force of the child have no x component, they're purely vertical. So we don't know what T1x is, we don't know what T2x is, but we know they have to add up to 0, and therefore they have to be exact opposites. We could even just subtract 2tx from both sides and say T1x equals the opposite of T2x. In fact, we could even fill in the values we know here. T1x we know is negative root 3/2 times T1. And that must equal negative T2 times sine theta2. So that tells us one equation describing how our 3 unknowns, T1, T2, and theta2 are related to each other. Meanwhile, if we also look at the y components, what forces have y components here?
All of them?
Yeah, so for the y component equation, we'll need to include all 4 of them. Let me put that separately. So the x components add up to 0. Separately, we can also say the y components add up to 0. So we have t1y plus t2y plus fgy plus fcy adds up to 0. And if we fill in our substitutions there, t1y and t2y, we can write in terms of the values we got here. For instance, t1y we know is 1/2 times t1 magnitude. So t1 times 1/2 plus, and t2y, we don't know t2, but we can at least write this as t2 times sine of theta 2. Plus force of gravity y component would be, since it's downwards, what would we call that?
Negative.
Yeah, so negative 60 newtons, and force of the child is also downwards, so negative 200 newtons. And again, those have to add up to 0 because there's no acceleration in the y direction. So this gives us a second equation that relates our three unknowns, t1, t2, and theta 2. And we still don't have enough information to solve, but we could at least rearrange this a little bit. For instance, how could we get rid of these numbers here on this side of the equation?
Like combine them?
Yeah, we could combine them. We'll get negative 260. And then how could we get rid of the negative 260 there?
Move them to the other side.
Yeah, or add 260 to both sides. So we get t1 over 2 plus t2 times sine theta 2 equals 260 newtons. So we still don't know what t1 and t2 are, but we at least know their y components have to add up to 260. And intuitively, I think that's just because it has to cancel out the 260 downwards forces from the child and gravity combined. So again, we still don't know what these three unknowns are, but we at least now have two pieces of information describing how they're related. We know that t1 and t2 and theta 2 are related by this equation and also by this equation. But we've got three unknowns, so we still need one more equation. We need three equations to solve for three unknowns. So what's one other equation we could write here?
We could do a torque equation. And
yeah,
should we make like the reference point the T2 point, because then we only have tension 1 unknown. And
yeah, I would do that. You can, I mean, physically you can choose any location as the pivot point. If the object is not rotating and is not going to start rotating, then any point could be used as the pivot point. But it's very useful to choose a pivot point where there are lots of unknowns that you don't have to worry about, or you don't want to have to worry about, because what do we know about the torque caused by tension 2 if we choose tension 2 as the pivot point?
It's going to be 0.
Right. Any location you choose to call the pivot point, if we call this point the pivot point, any force acting at the pivot point produces 0 torque. Because how do we usually calculate torque?
Either R perpendicular times F, and that would be 0. Or there's three equations, but yeah, they would all be 0.
I would say that probably the most universal one, the most foundational one, I guess, would be R times F times sine theta. All the other ones are just variations on that, I would say. So you could also describe this as R times the perpendicular component of the force, or force times the perpendicular component of the radius. Because the sine theta, if combined with either one of those variables, trigonometrically calculates the perpendicular component. So F sine theta is the perpendicular component of F. Or if you combine R times sine theta, that tells you the perpendicular component of R. But either way you look at it, I think probably if we look at it with this top equation here, RF sine theta, what's going to happen if you're talking about any force at the pivot point? What happens with that equation?
It becomes 0.
Yeah, because if you're at the pivot point, the distance from the pivot point is 0. And if the distance from the pivot point is 0, the whole thing becomes 0. So any force at the pivot point produces no torque at all. Likewise, if you've got any force pointing straight towards the pivot point or straight away from the pivot point, even if it's located somewhere else, any force that's parallel to the moment arm produces sine theta would be 0. So that would produce no torque either. So generally, if you've got the option of where to choose a pivot point, you want to choose a location that's the location of lots of forces you don't want to have to worry about, or a location that lots of forces you don't want to have to worry about are pointing towards or pointing away from. In this case, it would be nice if we didn't have to worry about T2, because T2 has a lot of unknowns. We don't know the magnitude, we don't know the angle. If we put our pivot point at that location, the only unknown we have to worry about is T1. So let's use that, using T1 as, or using the right side of the bar as our pivot point. We can now write out a torque equation relative to that pivot point. So let's try that. If we have all the torques have to add up to 0, and why is that, by the way? Why should we expect all the torques to add up to 0?
It's not rotating.
Right. And more importantly, it's not rotationally accelerating. Even if it was rotating, if it was rotating at constant velocity, we would expect total torque to be 0. But if it starts off not rotating and continues to not rotate, then there's no rotational acceleration. So we assume total torque is 0. And assuming that the right side is the pivot point, what forces are exerting torques here?
Gravity, the child, and tension 1.
Yeah, so we'll have torque from gravity plus torque from the child plus, let's call this torque 1, the torque from tension 1. And those have to add up to 0. And keep in mind, these are vectors. So we've got to take direction into account. However, in this particular problem, all the torques are going to be in only what kind of directions?
Like in or out?
Yeah, in this particular problem, the torques are all going to be straight in or straight out. Because in general, the torque has to be, the torque as a vector has to be perpendicular to the moment arm and perpendicular to the force. So for each of these, if we draw in the moment arm, like we've got the moment arm from the pivot point to the location of the force, and the force pointing straight down, or this moment arm to the location of the center of the beam and gravity force pointing straight down, or this moment arm all the way to the other side of the beam and tension force 1. In all those cases, if you think of this geometrically, the moment arm and the force vector form a plane. Anytime you've got two vectors in two different directions, they form a plane. The third vector, the torque, has to be perpendicular to that plane. So if you've got moment arm and force creating a plane that's a vertical plane, like the plane of the screen in this case, the torque has to be perpendicular to that plane, which means either inwards or outwards in this case. But yeah, in general, the torque has to be perpendicular to the radius and the force, the moment arm and the force, based on the way we define torque. So in this case, the only options are straight in and straight out. And of those, how would you decide which it is? Like, let's say for force of the child, how would you decide whether that torque is inwards or outwards?
Using the right hand rule, it would be out.
Yeah. Torque from the child, you curl your fingers in the direction, or you point your fingers from the pivot point towards the location of the force, curl in the direction of the force, and your thumb should now be pointing outwards. So torque from the child will be outwards, which we would usually draw as a circle with a dot in it. And what about the torque from gravity?
It's also out.
Right, that's going to be the same pattern. So also outwards. And torque from tension 1?
In.
Yeah, tension 1's going the opposite direction in terms of trying to make it rotate the opposite direction. So we would draw that as a circle with an X in it, representing an arrow pointing away from the viewer. And in terms of the arithmetic here, the algebra, that just means we'll treat one of those directions as positive and the other direction as negative. Doesn't really matter which is which. For convenience of the algebra, I usually treat a direction associated with an unknown we're trying to solve for as positive. But it doesn't have to be. You just choose a direction to call positive and the other direction to call negative. But for convenience, let's say we're treating outwards as negative and inwards as positive here. In that case, when we fill these in, we can calculate the torques using any of these three formulas, whatever is most relevant. Since we have an angle, we could write it as r times f times sine of that angle. Or you could think of it as r times which of these components, if any, counts as perpendicular to the radius?
Y component?
Yeah, the y component is perpendicular to the moment arm. Because the moment arm, this blue arrow I've drawn here, notice that the y component is perpendicular to that direction. So you could write the torque from tension 1 as the moment arm times just the perpendicular component of the force, which would be T1y. So T1, the torque for T1 could be written as tension 1 times the radius. And what's the radius? What's the moment arm from the pivot point all the way to that location?
1.8.
Yeah, that's the full 1.8 meters, the complete length of the beam. And then we could write it as moment arm times force times sine of the angle between them, 30 degrees. Or alternatively, you could write it as moment arm, 1.8 meters, times the y component, which is the perpendicular component. But what do we find is the y component of T1 anyway?
It's the T1 sine 30.
Right. So these methods both lead to the same result. T1 sine 30 is the y component. So if you write r times f times sine theta, you are effectively writing r times the y component, the perpendicular component of T1 anyway. So that's torque 1, tau sub 1. Torque 1 is 1.8 meters times the unknown tension 1 times sine 30 degrees. And sine 30 degrees we also know as 1/2, so let's fill that in as well. Sine 30 degrees, 1/2. Meanwhile, for gravity and for the child, for gravity, what's the radius going to be?
0.9.
Yeah, halfway to the end, because the gravity is located in the center. So halfway across the beam is going to be 0.9 meters. So for gravity, we've got 0.9 meters times, and then the force, 60 newtons. And what's the angle between the moment arm and the force of gravity?
90.
And sine of 90 degrees would be?
1.
Right, so we just had 0.9 meters times 60 newtons times 1. You could also think of it as r times f perp, but since the moment arm is already perpendicular to the force, the perpendicular component of the force is the whole thing. Same with tension or the torque for the child. We've got, what's the moment arm here? How far is the child from this pivot point?
0.3 meters.
Right, because we're told that the child is 1.5 meters from the left end point, so that'll be 0.3 meters from the right end point. So that'll be 0.3 meters times the force, 200 newtons. And once again, they're perpendicular. The moment arm vector and the force vector are perpendicular, so we'd have just sine of 90, which is 1. And then we should assign the positive and negative signs based on the direction convention we set up earlier. Anything pointing outwards, we're going to call negative. Anything inwards, we're going to call positive. And then we'll add those together. And the sum should be 0. So that's our torque equation, that the torque from gravity plus torque from the child plus torque from rope number 1 adds up to 0. Any questions on that equation so far? And at this point, we now have a system of 3 equations. This one, and this one. 3 equations and 3 unknowns, T1, T2, and theta 2, means we should be able to solve this system of equations. And you can use any method from substitution or elimination or matrix techniques to do that. But in this case, it's made significantly easier by one very useful fact. What do we know? What do you notice about this third equation, the torque equation we just wrote out?
It only has one unknown, so you can solve for tension.
Exactly. Starting with this equation in terms of the algebra involved is going to be much easier because it has only one unknown. And why is that? Why did this equation only have one unknown?
Mostly because gravity and child don't only have the one component, and we already had the angles, so.
Yeah, those ones are known. But we still have a lot of unknowns in tension too. Why did those not show up in this equation?
Oh, because there's no torque at that point, since that's our reference.
Exactly. And that was our choice, by the way. We chose to call that location the pivot point. Ultimately, this is why that was a good choice. Because choosing this location with lots of unknowns as our pivot point means none of those unknowns show up in the equation. The only unknown that does show up is the unknown tension from the other side of the bar. So this is a very useful thing to think about when you're choosing a pivot point, when you're setting up the situation. You know you're going to eventually end up with a system of equations. Forces add up to 0, torques add up to 0. So if you have a choice of pivot point, choose a pivot point that is going to make your torque equation have as few unknowns as possible. Ideally, just one. That way, it's much easier to solve that one equation for that one unknown, and then fill that into the other equations, and that will make those easier to solve as well. So let's try this out. How would you isolate T1 here? Or maybe we should simplify a little bit first. You got 0.9 times 60, that's going to be 54. So negative 54 Newton meters. And then 0.3 times 200 would be 60, so negative 60 Newton meters. And half of 1.8 would be 0.9 meters times T1. And then how would you isolate T1 there?
You would do the negative 60 minus 54 added to the other side and then divide by 0.9.
Yeah, that should work. And 54 and 60 would be 114. So we add 114 Newton meters to both sides. And yeah, divide by 0.9, that's same as multiplying by 10/9. So T1 is 114 times 10/9. Meters cancel out, so we just get, so 114 times 10/9. What is that kind of?
I got 126.7 newtons.
Sounds good. 126.7 newtons. So that would be how strong tension 1 is. And notice that that's not one of the components of tension 1. This is tension 1 because we already incorporated direction based on the sine 30 or 1/2. So tension 1, the strength of tension 1, the magnitude is 126.7 newtons. We could then, if we wanted to calculate the x and y components as well. Those are going to show up naturally in the force equations, though, when we multiply T1 by negative root 3 over 2 or by 1/2. Any questions on tension 1 so far?
No.
So let's see if we can fill those back in. I think I may have made a mistake in one of those force equations, because it looks like I've got T2 sine theta 2 in both of these. One of those should probably be cosine. Do you see which one should be cosine instead?
Yeah, the x equation.
Yeah, let me fix that. That should have been cosine the whole time. So we've got our force in the x direction equation, our force in the y direction equation. What can we now do with those equations?
We can use each equation and have only one. Well, we can solve for each component, and then we could use inverse tangent to find the actual theta.
Yeah, that should work. In fact, it might be more useful, instead of writing it as T2 cosine theta 2 and T2 sine theta 2, it might be better to just leave it as T2x and T2y for now.
Yeah.
And then we can fill that in later as needed. Sometimes it's easier to just write everything in terms of the components. And note that that's still the same number of unknowns. You could treat T2 and theta 2 as the unknowns, or you could treat the components, T2x and T2y, as the unknowns. Both ways of writing the vector represent the same information. It's just different ways of writing it. So let's go ahead and leave that as T2x and leave this as T2y. So we know T1 times negative root 3 over 2, that is the x component of T1, has to equal T2x. We need a negative sign there also, though, because we had T1x is the opposite of T2x. T1x is negative root 3 over 2 times our T1, 126.7 newtons. That has to be the opposite of T2x. And if we fill in T1, which we now know is 126.7 newtons, what does that tell us about T2x?
It's the opposite, so it's positive 109.7 newtons.
Yeah.
Or positive 127 times root 3.
Right, and that works out to, do you say 109?
I got 109.7.
Okay, so that will be T2x. Let's fill that in the force triangle, 109.7 newtons. And likewise, we can solve for T2y as well, because we know T1, once again, is 126.7. And half of that should be the y component, since sine of 30 is 1/2. So 126.7 newtons over 2 plus T2y, which is unknown, equals 260. How would you isolate T2y there?
You would just subtract the.
Yeah. Subtract that 126.7 over 2. And what do you get there? A little less than 200, I think.
Yeah, when I did it, I got that T1y is 114. So then I was getting 146, but now I'm trying to figure out.
T1y
would be.
Well, T1y should be exactly half of T1, because this is a 30, 60, 90 triangle.
I was looking at my torque equation, adding the 1.8 before, so I see where I missed it.
Oh yeah, that could do it.
So it would be like 196, around there probably.
Yeah, that sounds about right. So that's T2y. And at this point, we now have the x component and y component of tension 2. So you can use inverse tangent to find the angle and Pythagorean theorem to find the magnitude as usual. And at that point, we have the strength of tension 1, the strength of tension 2, and the angle made by tension 2. Any other questions on that so far? And by the way, we could have done this exact same problem by choosing any other location as the pivot as well. You could choose the left side for the pivot. The only problem would be that you'd now have more unknowns in that equation. You'd have unknown x component and unknown y component. I guess the y component's all that would really matter, though, because we'd have perpendicular. So that would still only have one unknown, the y component. But that would make the other equations a little more difficult to solve. Still solvable. You still get the same result. It just might be a little more trouble. You could even choose some arbitrary point where nothing's really happening as the pivot. You could choose like a location 1 meter from the end as a pivot point. The math would be more complicated. You just have a much more complicated system of 3 equations, 3 unknowns to solve. But the solution would still be the same. You'd still get the same end results for the forces. It just takes more work to get there. So generally you want to set up the system so that the resulting equations are as easy to solve as possible. And was there anything else we needed to figure out here? If the length of the bar was longer while the weight stayed the same, and the girl was still hanging the same fraction of the bar away from the left, would the tensions increase, decrease, or stay the same? So if we just take this whole system, this whole bar, and stretch it to be longer, but we keep the same weight. Any thoughts on that? If we take the same bar, make it longer, but keep it the same weight and keep the girl still hanging the same fraction of the way along the bar, what would you expect to happen there?
I feel like it would stay the same because the length, you don't actually really need to know the length. You just need to know the relative, how they're related. So if the relationships aren't changing, then the forces won't change.
Yeah, I think it's really all about those proportions. Because what was the only time in this entire algebra here? What was the only time we actually used the lengths?
When we're calculating torques.
Right. We had tension. The 0.9 meters, the 0.3 meters, the 1.8 meters. If we rescale this, if we make this bar longer, that is going to change all of these lengths. But if we assume that the girl is still hanging the same proportion, the same fraction of the way along the bar, those are all going to change proportionally. Like, let's say we make the bar 3 times as long. All of these lengths get 3 times as big, but that's effectively just multiplying both sides of the equation by 3. It doesn't change the result. It doesn't change the solution of the equation. In fact, if we had ignored the length, if we had said, like, let's say the length is L, then the force of gravity would be half of L along the length. The tension force 1 would be all of L along the length. So we'd have half of L, we'd have L, and the child is what, 6 of the way? So L over 6. And if you fill those in, if you just replace these distances with L over 2, L over 6, and L, you're still going to get the same result. When you divide both sides by L, all the L's are going to cancel out. So ultimately, the length does not matter as long as everything is still the same ratios. The proportions are really what matters here. Any other questions on that? Or any other general questions on torque or free body diagrams like this?
I have to go because I have a meeting, but maybe next time, can we just do a few practice, like finding R perpendicular versus F perpendicular?
Yeah, and feel free to email me any if you have any other examples you want to try out. Go ahead and email those to me or send them in Discord.
And okay, thank you.
You're welcome. See you later.